This is Mr. Anderson for Kellogg Community College, and we're going to talk to you about the basics of logarithmic functions. This is for Chapter 9, Section 3 of Math 121, Intermediate Algebra. Now, we're going to start off with just a basic exponential function. So, if we look at y equals 2 to the x, and we plug just some numbers in for x, let's plug numbers, let's say 0 and 1, 2, 3, 4. If we plug 0 in for x, 2 to the 0 power is going to be 1. So that would be 2 caret 0 on your calculator. Then if I type in 2 caret 1 on your calculator, then I get 2. And 2 caret 2 on the calculator is going to be 4, 2 to the third is 8, and 2 to the fourth is 16. And this is going to go on, as for every power of 2, it's going to double the previous entry there. So this is the exponential function in the world where the numbers double every time. Now, what you have here is the inverse of that equation. This is where the x is y is flipped. And the easiest way to graph something like that is to flip the x and y tables from this parent equation right here. So this inverse of the equation, so the inverse of this one, is going to end up being our logarithm equation. Because our logarithm, which can't be typed into the calculator, you can't just type this into your calc because there's no x equals button, this logarithm is going to be done by hand on the next page. But what this is to illustrate here is that we have a logarithm which is the inverse, or logs are the inverses of the exponential functions. Now, we're going to see that graphically in the next on the next page, but also there's some different notation to use with logarithms. And some of you might be wondering, well, why should we use a log? And the why part of that, why we should use a log, is going to be at the end of this first page here. But first of all, let's kind of get back to this idea that logs are the inverses of exponentials. So let's put that back here again. Logs are the inverses. I might be referring back to this in just a bit. So what we have here is this exponential equation is equivalent to this log equation. But the format is different, and we got to teach you the format. So the first thing you notice is that this is y equals 2 to the x. So we are in the base of 2. Now the base means that this is what our system is going to move by. So in the table above, our base was 2, so our pattern goes 1, 2, 4, 8, 16, 32, 64. So our log is going to be working in base 2. Now, the y of the problem is going to be next to the 2, and this is going to be read as log base 2 of y is x. So you may want to write that down if you want to help yourself say these out aloud. Log base 2 of y is x. Now, what this is asking me is this question. What power of base 2 gives me the value of y? Now, if I look over here, it's easy to say that based on this picture. What power of 2 gives me y? The answer is going to be x, of course. Now, the reason why these are written this way and why this is so important to see it this way is because you'll see that my exponent is my answer. So in this problem, you'll see that the exponent is not the answer. It's really the total. So here, another way to write the problem is having this x as your answer. And we're going to see why that is more and more important. Because still some of you are thinking like, well, shoot, I've got this beautiful equation over here. How come I have to change it into something like this? And that will be explained in just a moment. So y equals 3 squared. So what's my base? My base is that the powers that I'm working with. So my log is base 3. So this number system is going 1, 3, 9, 27, 81, 243. And this is going to be my letter y, and this is going to be 2. So if I was to write this out in words, I would say, what power of 3 gives me y. So what power of 3 gives me y? And that's the answer to that problem is 2. Now, some of you now know the answer y. Y is 9. So now if I know the answer is 9, because 3 squared is 9, that changes the problem to what power of 3 gives me 9? And the answer is 2. All right, now what you might want to do is why don't you pause the video and try to plug in the number down here, the number that goes inside the parentheses, and then the answer. The number that goes down here is 4. It's the base. It's the power. The base is 4 right there. So this universe is going to be going by 4s, which is 1, 4, 16, 64, 256, and so on. The number that goes inside here is 64. And the number that goes on the outside is 3. Which means, what power of, if I was going to write a sentence on this, what power of 4 gives me 64? And the answer is 3, because 4 cubed is 64. Now we're going to convert from log to exponent form. So what this is going to be is let's see, we're going to take our base, which is 5, our power, which is x, because the answer is always the power, and then the y equals will go either in front or in back, because that is due to the symmetric property. I can write it as 5x equals y or y equals 5x. So again, this is asking 5 to the what power will give me y? And there it is. So this one here, 2 to the 4th power will give me y. I'll do that again just to see the pattern through. 5 to the what power will give me 125. So again, converting from here to here, it's saying the same things but just written in a different way. This way, the exponents are not isolated, and here the exponents are isolated. Well, why do we need the exponents isolated? Because why do we teach exponentials? And I think we know why exponentials are so good, because we can do story problems with them, especially interest rates, growth rates, and all that other fun stuff. But why do we have to know what a logarithm is? But let's solve for x within the log base 3. So 3 to the what power is 9? Well, we can know that answer. 3 to the what power is 9? That's 2. 3 squared is 9. 3 to the what power is 27? Well, that's going to be 3. 3 to the what power is 81? Well, that's going to be 4. 3 to the what power is 50? Oh no, 3 doesn't actually make 50 evenly through exponential functions, but we know it's between 3 and 4. So this gives me a problem right here. So x is going to be between 3 and 4, but we don't really know when exactly it is between 3 and 4. And that is actually an important question, especially if you're working in medicine or working in engineering, and you need something to know exactly when you will have 50 items that are being tripled. Like, when will that moment in time be when you will have, if something's tripling, exactly 50? Well, we cannot get an exact answer for this problem, so sorry about that. Cannot get an exact answer for it. However, what we are going to do, though, is learn in future steps what those answers are. Now, to finish up this first page here, is I want to convert those 4 problems here, these into log notation format. So let me go and do that now. So this is going to be log base 3 of 9 is equal to x. And we know that answer is 2. Here we have log base 3 of 27 is equal to x, and we know that answer is 3. You try the next one. You can pause the video and see what you write. This is log base 3 of 81 is equal to x, and we know that answer is 4. But this last problem right here, log base 3 of 50, we don't know that, and we're not going to know that until we figure out something called the change of base formula that we'll learn very soon in a future video. So in conclusion, this equation is equivalent to this equation. It's just that here the x is all by itself. I'm sorry, no, the the x, crap, sorry about that. In this equation, the exponent is all by itself, and that's really important because sometimes we want to know that exact moment when we will get a number for my x. All right, so let's go take a look at the second page here. We're going to do a couple of simplifying problems, and this deals with that equation, and I think it's probably best if you write down a couple things here, because when they ask you to simplify this is really what the question is asking. What power of 10 gives me 10? What power of 10 gives me 10? And the answer there is 1. Now this is an important shortcut because we're going to see that log base x to x will always be equal 1. Because this is asking what power of x gives me x, the answer is 1. So when you see this, we're going to circle it and turn it into 1. All right, now take a look at this. What power of 10 gives me 100? Well, if I think about the powers of 10, the powers of 10 would then be, let's see, I got 10 to the first power is 10, 10 to the second power is 100. Oh, wow, 10 to the second power is 100, so the answer is 2. Let's go ask this question. What power of 3 gives me 9? And we just did a problem like that on the previous page. The answer is 2. Now things get a little weird here because it says what power of 8 gives me 64? Now, or 1 over 64. Now, the trick with fractions here is that if you think of this instead of a fraction, think of it like this. The log of 8, the log base 8 of 64. That answer is 2. And the answer is 2 because 8 to the second power is 64. But now we have a fraction. So what I would really like is I'd like to get 1 over 64, and to do that I can use a negative exponent. So this 8 to the negative second power is 1 over 64. Now for those of you who just felt like you were blown out of the water by this, just remember that there is something called the change of base formula coming up that will make this problem a lot easier. Another way you can do it is you can type into your calculator y equals 8 to the x and scroll on your x and y until you see where you get 1/64th, or that decimal equivalent. And you will see that if you go from 0 will be 1, 1 will be 8, and 2 will be 64, negative 1 will be 1/8, and then negative 2 will be 1 over 64. Now these will be decimal equivalents on the calculator, so they're a little bit harder to find, but that's really where that comes up. Now again, if you still felt that this has been kind of rocking your boat here, note that the change of base formula, which we will learn later, will make this problem a lot more simple. All right, here's the question here. What power of 9 gives me 1? Now this makes you remember a rule. Anything to the 0 power is 1. Now in problem number 10, you might be inclined to go 6 to the 9th power, and then ask yourself, 6 to the what power is this big number, and it's over 10 million? Well, think about it this way. 6 to the what power is 6 to the 9th? Well, that answer would be 9. Because if 6 to the 9th power is the 9th power. So 6 to the what power, 6 to the 9, and that would be 9. This also brings up a little shortcut that we might be learning later, that you see how we have the same base and the same answer there? So that's going to give me a 1. So this becomes 1 times 9, which is 9. And we're going to develop this a little bit later in the next section where we're going to be doing more and more simplifying. Okay, so now we look at this. 100 to the what power is 10? Now, if you try taking 100 and raise it to the first, second, third, fourth power, you're going to get numbers way bigger than 10. But you may notice that the square root of 100 is 10. Therefore, the answer is going to be the square root, or 1/2. See, the 1/2 power is the square root. So this is like saying the square root of 10 is equal to 100. Assuming all values are positive. Now this last problem right here is going to be 3/4. Wait, where was the explanation on that one? I don't really want to work through the entire explanation, but I do want to say that if you do take 16 to the 3/4 power, or 0.75 power, or 75 hundredths power, you will get 8. But you might be saying, but where is the explanation? Yeah, we're going to learn the change of base formula, so for some problems like this, you might have to resort to the back of the book. But even in problems 8, 11, and 12, where the answer wasn't an obvious whole number answer, you will get a change of base formula that will make that a lot more simple. Now it's time to do some graphing. How do we graph a log? Now, when you go to your calculator and try to use the log system, what's unfortunate about that is that you're not going to get a way to do that on the screen, and I'll show that to you. By bringing up your graphing calculator, your log button doesn't allow, standardly doesn't allow you to put in a subscript. Like, you notice that you can't put a base 2 in there, so trying to draw the log base 2 will not be possible. In fact, your calculator loves log base 10, which we'll talk about in the next section. So you can't actually graph this the way that we have. So here's how you graph a logarithm. You first of all graph its equivalent, which is y equals 2 to the x power. All right, so there's the exponential. So there's the exponential of the log. Now, how did I know it was base 2? From the little number here. Now, I'm flipping my x and my y, and I'm using this equation right here, and I'm not going to graph this. I'm just going to use the table. So the first step is to use the table for your logarithm. So step 1 to graph a log is to first of all graph the exponential. Now the exponential is the inverse of the logarithm. So we're going to have our x and y values, and our x and y values are going to be negative 2.25. Sorry, that didn't show up there. Negative 1 and 0.5, 0 and 1, 1 and 2, and I'll put another one on there for good measure, 2 and 4. So there's your exponential, or y equals 2 to the x power. Now what I'm going to do is, since I know from the previous side of the worksheet that the inverse of an exponential is a log, I am going to flip-flop the table. So step 2 is to flip-flop the table. So flip the table. Now, don't flip the x and y, flip the numbers. So 0.25 and negative 2, 0.5 and negative 1, 1 and 0, 2 and 1, and 4 and 2. Sorry, caught me thinking there. Then step 3 is to graph. And only graph this second table, because that's your logarithm. Now, if you do graph your exponential, you will see how they're inverses of each other, but it's not necessary. They're only asking you to graph the log. So let's graph the log. So it's this table 2 right here. So we're going to graph this. So x is 0.25, y is negative 2. X is 0.5, y is negative 1. X is 1, y is 0. X is 2, y is 1. X is 4, y is 2. And there is your beautiful logarithm. Now, if you did graph your exponential, it would swoop like this, which would be a reflection over the y-axis. We looked at that on the previous video. But you'll notice that these logarithms do not cross the x value. So the domain of your logarithm is always going to be x greater than 0. That's going to be important when we start solving for logarithms. All right, let's go take a look at the next graph. Okay, so what we have to do is we have to graph our exponent first. So that instead of using base 2, we're going to be in base 4. And take a look at the table. All right, some of those, I can't go too far. You can see that even if I go to 2, I'll be off my grid there. So I'm just going to graph these 4 points, negative 2, negative 1, 0, 1, 2, for my table. So let's go to my table here. So step 1 is to draw down the table. Again, graphing optional of the original function. So what we have is negative, this is my x and this is my y. Negative 2, negative 1, 0, and 1. I'm not going to go further than that. This is negative 2 is 0.0625. Negative 1 is 0.25. 0 is 1. 1 is 4. Now, the second step I'm going to do is flip the x and y. So here's my x and y. I'm going to flip them around. 0.0625, negative 2. 0.25, negative 1. Then we have, let's see here. Caught me thinking here. 0 and 1, and then 4 and 1. So this is what I'm going to plot. This is going to be my log. This is my log base 4 of x. So let's see. 0.0625 is just really close to 0 there, and we're going to go down 2. So it's going to be like snugging up to that y-axis, but technically wouldn't touch it. 0.25 and negative 1 is going to be right here. 1 and 0, and 4 and 1. So here is my log base 4 of x, graphed perfectly. Okay, we got some problems to rewrite but not solve. So let's go and look at how these will be rewritten here. Alright, so let's go and look at this. These will go pretty quickly here because this is going to ask, let's see here, we got to write them as exponential equations. So 6 to the second power is 36. Yeah, that seems right. Let's see here. 10 to the 0.4771 or 4,771 ten-thousandths is equal to 3. How about this one here? This is m to the a power equals p. Map. All right, or PMA, I guess, if you wrote it the other way around. You could also write this here. Let's go with, let's see, c to the negative w power is equal to m. Or you could write it m is equal to c to the negative w. All right, going to continue on with some problems on this next side here. It says rewrite as equivalent and as an equivalent logarithm, do not solve. Okay, some more quick problems here to do some rewriting here. This is going to be this is going to be my pen not working. Okay, log base 2. Inside the parentheses is going to be 132, or 132nd, sorry, and negative 5. So this is asking what power of 2 to the negative 5th power is 1/32. All right, so what's the base here? The base here is going to be 10. And then we're going to write, wait a second, you don't see me writing 10 down to you. I can't. No, actually, log base 10 is actually written as log. You and I work in base 10. We count from 0 through 9, and then we start over again. So we are in log base 10 because we are doing things, counting our normal numbering system. So we don't write log base 10. We just write log. So log without the 10 in the 10 in the little area right here is log base 10. So this is going to be 2, and then this is going to be 301 thousandths. So log base 10. So 10 raised to the 301 thousandths is 2. All right, this is log base y to make t. So y raised to the t power will give me x. All right, now this is an interesting one. This is log base e. Now e is a special number that we're going to investigate in a future section. So what this tells me is that if I take e and raise it to the negative second power, I get this decimal, 1,353 ten-thousandths. Now what's important about that is that log base e has another name, and it has ln, which is called natural log. And your natural log key is on your calculator. So if you want to type in things using ln, and the same thing up here, you can actually do some of the work. But that is going to be for a future a lesson later, that log base e is written as natural log. So don't worry, we'll talk about that soon. Now for the last problems, there is a little worksheet error. For problems 23 through 25, what got cut off of the worksheet here was the word solve. So we actually are going to rewrite these and solve them. So this is going to be 5 to the what power is 25. Now using just some normal thought here, x is going to be equal to, that's going to be 2, right? Because 5 squared is 25. All right, so here we have x to the 1/2 power is equal to 9. Now, we learned earlier today, I talked about the 1/2 power. The 1/2 power is the square root. So the square root of x is equal to 9. All right, so what number raised to the 1/2 power is 9? I know you want to say 3. 3 isn't right. The square root of 3 isn't 9. The answer, if I square both sides, x is equal to 81. So my answer is the log of 81 of 9 is 1/2, or 81 square rooted is 9. So 3 is a common mistake here, but the answer is 81. All right, now this one here, let's go with this. This is, let's see, 8 to the 2/3 power is equal to x. All right, so thankfully we can go to our calculator and do this one. So for the end of this worksheet here, we're going to go to our calculator and say 8. Oh, I got to grab my calculator. Come on, you. There we go. So to finish this off, we're going to go to a clear screen and go 8 raised to the 2/3 power is going to be equal to 4. So the answer to this problem, let's go back to my screen draw here. I'm going to say that log base 8 of 4 is 2/3, which means 8 to the 2/3 power is 4. Wow, thanks for watching, and I'm hoping this logarithm video helped out a little bit, and please email me if you have any questions. Thank you.